Today, we're going to talk about the mole and dimensional analysis. Now, the mole is a unit of measurement that we use in chemistry. It's very, very useful because molecules and atoms in chemistry are teeny, teeny, tiny. So when we talk about, let's say, water, or we talk about oxygen, or we talk about carbon, we're not talking about one water molecule, one oxygen, one carbon. We're talking about a whole lot of them because they take up so little space. So it's a way of counting those. Okay, so substances can be measured in different ways. We can count them. We can say we have 5 apples. We can say we have a dozen eggs. We can weigh them. We can say we have 2 pounds of bananas. Say we have 16-ounce box of cereal. And we can see how much space they take up, volume. We can talk about milk in terms of a gallon of milk, a pint of cream. These are different ways of measuring things. Well, in chemistry, when we talk about atoms or we talk about molecules, we can also talk about them in different ways. We can count them, we can weigh them, and we can see how much space they take. And all those things are related to the mole. The mole can be related to each types of these measurements. We can count them, we can weigh them, we can see how much space, volume they take up. Okay, what we're going to talk about today is the first bullet point, counting. Okay, we're going to count them. We'll talk about mass and volume in a later lesson. Okay, currently, when we talk about the mole in this class, it is the amount of any substance, whether it's an atom, something like just a helium by itself, or a molecule, something like carbon dioxide, or what's called a formula unit, an ionic compound, something like sodium chloride, which is a ionic compound. Table salt, sodium chloride is table salt. We can talk about the amount of any substance that contains as many elementary entities as there are 12 grams of pure carbon. So the mole has its reference point is carbon. Why carbon? Because carbon makes up everything that's important to us. So the reference point for the mole is carbon. It says if you have a carbon molecule, it's going to weigh 12 grams. 1 mole of it will weigh 12 grams. That is also the atomic mass unit of carbon if you look it up on your periodic table. So the mole is relative to carbon. Okay. It's a unit in chemistry. That's a bridge between the atomic and the microscopic world. It's how we get from talking about one water molecule to a bucket of water. It's that bridge. It's a thing that links them. And we can use links in dimensional analysis. Okay? So in Latin, the word mole means a huge pile. So let's define what a mole is. A mole is defined as 6.02 times 10 to the 23 of anything, in chemistry specifically of atoms, of molecules, or of formula units. Okay, an atom is something straight off the periodic table, like an element. A molecule is something that is what's called covalently bonded, like water or carbon dioxide. Formula unit is something that is an ionically bonded compound, like sodium chloride, your table salt. Calcium chloride, what they salt the roads with when it snows up north. But 1 mole is equal to 6.02 times 10 to the 23 anything. So if I say I have a mole of frogs, that means I have 6.02 times 10 to the 23 frogs. If I say I have a mole of atoms, of helium atoms, that means I have 6.02 times 10 to the 23 atoms. Okay, so what does that look like? This is what this number looks like. Okay, none of us want to write all those zeros down. why we use scientific notations. One of the reasons we use scientific notation in science is so that we can talk about really big numbers using a smaller number. Okay, this is 602 sextillion. Okay, so it's a counting unit. It's similar to a dozen, like a dozen is equal to 12. A mole is equal to 6.02 times 10 to the 23. Okay. We know this number to many more significant digits than this. It's a measurement, and we know it to many more significant digits than these three. But for this class, we'll either use 2 or 3. I mean 3 or 4. You will say 6.02 times 10 to the 23, or 6.023 times 10 to the 23. This number right here is named in honor of Amedeo Avogadro. Oh, I don't know why it's blinked out. His name is Avogadro. Avogadro. Kind of sounds like avocado, but it's not. Avogadro. He was the person who studied quantities of gases. He was looking at gases, and he discovered no matter what gas there was, it was always the same number of molecules present. Didn't matter whether you had hydrogen gas, you had carbon dioxide, you had oxygen. Any gas that you had, there was always the same number of molecules present when you were looking in a confined volume. So how exactly big is a mole? Just to give you perspective. Okay. If you had a mole of soft drink cans, like mole of Coke cans, the surface of the Earth, it would cover the surface of the Earth to a depth of over 200 miles. So if you covered the entire surface of the Earth with soft can drinks and start stacking them using a mole of soft can drinks, it would cover it for 200 miles, over a depth of 200 miles. If you had an Avogadro number of unpopped popcorn kernels, just like little popcorn kernels, and you spread them across the United States, the country would be covered in a depth of over 9 miles in popcorn kernels. So you cover the United States in popcorn kernels, you would have a depth of 9 miles. It's a huge number. If you are able to count atoms, if you can count the number of atoms at a rate of 10 million per second, so you're counting by 10 millions, it would take you 10 billion years to count all the atoms in one mole. It's a huge number. That means your atoms are so small that when we talk about them at this huge number. Okay. So this number, this weird number, it's not just some random number. Not just a number. It was a measurement. And the way it was originally measured was using the Millikan oil drop experiment. If you look in this PowerPoint, there's some hidden slides, and one of them talks about it there. It was looking at using this Millikan oil drop experiment. Since then, we have much better technology. We can use X-ray technology to measure it, but we know it's a measured value. It's a measured value with significant figures, but our technology is so good that they know it to many digits. So it will never determine your significant figures in a problem because it's always going to have way more than anything else you're talking about. Okay, so it's a measured value. Okay, so just to tell you again, it's just a measurement. It is a unit. It's a way of talking about things. So if you say you have a dozen cookies, a measurement, a dozen is a measurement. That means you have 12 cookies. But if you say you have a mole of cookies, 1 mole of cookies, you have 6.02 times 10 to the 23 cookies. If you say you have a dozen frogs, you have 12 frogs. If you say you have a mole of frogs, you have 6.02 times 10 to the 23 frogs. Okay? If you have a dozen cars, you have 12 cars. You have a mole of cars. You have 6.02 times 10 to the 23 cars. If you have, now let's throw in some chemistry words. If you have a dozen aluminum atoms, you have 12 aluminum atoms. But if you have a mole of aluminum atoms, you have 6.02 times 10 to the 23 aluminum atoms. It's a better measurement to use when we talk about aluminum atoms. Now, this is called an atom because it's one thing by itself. It's just aluminum. It's not chemically combined to anything else. So when you see the word atom, you know it's something that's by itself. Aluminum by itself. Hydrogen by itself. Carbon by itself. Okay? So note that the number is always the same, 1 dozen, 1 mole, but the mass is different. A dozen cookies is going to weigh much less than a mole of cookies. Okay, but we're not going to talk about the mass part today. Okay? When you're doing your problems, you can abbreviate mole with MOL. You can't abbreviate with just little m because little m by itself stands for meters. You must write MOL. You can't abbreviate it as ML because that's milliliters. Abbreviation for mole is MOL, or you can write the whole thing. It's not that much longer. Okay. So because it's an equality, we can use it as a conversion factor to convert in between moles or moles into particles, things like that. We use it as a conversion. Again, 1 mole is equal to 6.02 times 10 to the 23 atoms. 1 mole, an atom being something that's by itself, like aluminum. 1 mole is equal to 6.02 times 10 to the 23 molecules, something like carbon dioxide. A molecule is something where things are chemically combined in a covalent fashion. You don't know what that means yet, but I'm telling you. You see two things put together, like water, it's got hydrogen and oxygen. Carbon dioxide has carbon and oxygen. Those are molecules, okay? 1 mole is equal to 6.02 times 10 to the 23 formula units. That's also something that is chemically combined, but in what's called an ionic bond. And that would be something like table salt, sodium chloride, calcium chloride, magnesium fluoride, something like that. Okay? You must have this relationship memorized. You must know this is called Avogadro's number. Avogadro's number, and you must memorize it. Again, here it is again. Okay. You don't have to remember how many zeros to write down because it's told to you in the exponent. So let's do a problem. It says, how many atoms are in 1.22 moles of sodium? Okay, let's write down what's given first. Given to us in this problem is 1.22 moles of sodium. Na is the shorthand, is the symbol for sodium. Next, we write, what do we want? We want to know how many atoms of sodium there are. Okay? And we have a ratio that can link these two. We know that 1 mole of anything is equal to 6.02 times 10 to the 23. So if you have 1 mole of sodium, you're going to have 6.02 times 10 to the 23 atoms. Okay, so let's do our dimensional analysis. I'm going to write it over 1, write the given as that we know. Now we have to use our dimensional analysis. Well, I just told you 17 times that 1 mole is equal to 6.02 times 10 to the 23 anything. 1 mole is equal to 6.02 times 10 to the 23 atoms. Well, to do our dimensional analysis, we would write 1 mole of sodium, so our moles cancel out, is equal to 6.02 times 10 to the 23 atoms. This is our relationship. We want moles to cancel out. We're left with atoms at the top. So then, double check your units, like we've done every time. Your moles cancel out. What are we left with? Atoms of sodium. What do we want? Atoms of sodium. So we've set this up right. So now it's a matter of entering it into your calculator. You need to know how to enter exponents, and your answer should be in 3 significant figures. When you enter this into your calculator, you get 7.34 times 10 to the 23 atoms. Let's do another problem. How many moles are equal to 4.7 times 10 to the 24 molecules of CO? What do we know? We know 4.79 times 10 to the 24 molecules of carbon monoxide. What do we want to know? What's our unknown? We want to know how many moles of carbon. So let's write down what we know, put it over 1. We want molecules to cancel out. Molecules. Well, we know that 1 mole is equal to 6.02 times 10 to the 23 molecules. So we would put the 6.02 times 10 to the 23 molecules on the bottom, and you would be left with 1 mole on the top. Units cancel out. You're left with the 3 significant figures. Because this is 3 significant figures, you would be left with 7.96 moles of CO. Please enter this into your calculator. Make sure you can get this number. Again, if you are using the times 10 to the little caret 23 in your calculator, you must make sure to put this entire number in parentheses. If you are using the exponent button, you do not need to. You would just enter 6.02 E23. Okay, let's do another problem. Determine the number of atoms or moles. Determine the number of atoms and moles in aluminum carbonate. I need to fix this because I took the ions out. You have aluminum carbonate. This is what we're doing. We want to know how many atoms we have of each. How many atoms of aluminum do we have? How many moles of aluminum do we have? How many atoms of carbon do we have? How many moles of carbon do we have? How many atoms of oxygen do we have? How many moles of oxygen do we have? Okay, so this is what aluminum carbonate looks like. You got 2 aluminums, and you have these guys right here are called carbonate. We have 3 of those. See, 1 carbon, 3 oxygens. We have 1, 2, 3. This is what's called an ionic compound. So this is going to have what's called formula units. So we know you have 1 mole of aluminum carbonate. You're going to have 6.02 times 10 to the 23 formula units of aluminum carbonate because it's an ionic compound. Okay. If you have 1 mole of anything, you're going to have this number of that. Okay. So aluminum carbonate. If we look at our aluminum carbonate, how many atoms of aluminum do we have? We have aluminum and we have 2. We have 2 atoms of aluminum. Atoms. Okay. How many atoms of carbon do we have? Well, we have 1 carbon, but look, see this parenthesis? It's for everything. So that 3, you have 3 atoms of carbon. How many atoms of oxygen do we have? We have 3 times 3. We have 9 atoms of oxygen. So when we're talking about atoms, we're talking about things in the microscopic realm. Tiny, 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 tiny. Instead of talking about the microscopic realm, moles allow us to talk about things macroscopically large. So we can go back and look at the same thing. Let's look at aluminum carbonate. We have, instead of talking about atoms, we have 2 moles of aluminum. 2 moles of aluminum. We have 3 moles of carbon. We have 9 moles of oxygen. And that's when we talk about aluminum carbonate macroscopically in a large amount. Okay, so if you're talking about things microscopically, you're going to talk about them in terms of their atoms. If you want to talk about it macroscopically, like in the world where we live in, we talk about each of these guys in terms of their moles. But the numbers are the same. The weight is different, but the numbers are the same. Okay, let's do another problem. It says determine the moles of magnesium there are in 1.23 times 10 to the 24 atoms of magnesium. What's given? 1.23 times 10 to the 24 atoms. What do we want? We want moles of magnesium. What is our ratio? We know 1 mole of magnesium is equal to 6.02 times 10 to the 23 atoms of magnesium. If you have the word mole, it's going to be this number atoms in this case. So now let's solve our problem the same way we've solved every other problem. You write down what you're given, you stick it over 1. Now we use our ratio. What do we want to cancel out? Atoms. Well, so this guy is going to go on the bottom. If we do that, our atoms cancel out. If we use this part, then we have to use the other part, 1 mole of magnesium. If you look, atoms cancel out. You're left with 1 mole. Enter that into your calculator. This is what you get. If you get your atoms of magnesium canceled out, 3 sig figs, moles of magnesium. If you get a number that is times 10 to the 46, times 10 to the 47, times 10 to the 45, times 10 to the 48, in that realm, then you have a calculator mistake. Anytime you see a problem that has those exponents, 46, 45, anything around there, you entered something in wrong into your calculator. Make sure you can enter this into your calculator. Let's do one last problem. Determine the number of water molecules in 11.2 moles of water. Given 11.2 moles, molecules of water, that's what we want. And we have our ratio. 1 mole of water is equal to 6.02 times 10 to the 23 molecules of water. 11.2 moles of water. We write our given first. Put it over our 1. We want moles of water to cancel out. Very easy to confuse moles and molecules. Don't do it. Moles versus molecules. We want moles to cancel out. So this is the part that goes on the bottom. We want molecules to stick around. That goes on top. Moles cancel out. Your answer should be in 3 significant figures. You enter it into your calculator, and you get 6.74 times 10 to the 24. Moles cancel out. Molecules of water. We have not done anything different than we've been doing before. These have only been one-step problems. We're using the same dimensional analysis that we've always used. We've just introduced a new unit. A mole of anything is 6.02 times 10 to the 23 of that thing. A mole of water is 6.02 times 10 to the 23 molecules of water. A mole of calcium is 6.02 times 10 to the 23 atoms of calcium, because it's just one thing by itself. A mole of barium chloride is 6.02 times 10 to the 23 formula units of barium chloride. A mole of frogs is 6.02 times 10 to the 23 frogs. Okay? It's just a new unit, but nothing else is new. Okay, please practice.